So we've been looking at now Lorentz force and an application, a MEMS application that uses Lorentz force. Now we're going to have a closer look at coils and how they can be used in microsystems. Coils are actually, they use the Lorentz force, but do that by creating a 3D structure out of a wire. So instead of just using one wire and looking at the magnetic field around one wire, we're going to wind up the wire tip, as you can see here, several times. So and each contribution of the magnetic force of every wire is then added up. So you basically, n windings creates a magnetic field that's n times stronger than the magnetic field around one winding. The first thing that we can observe is that, of course, coils by nature are or must be 3D structures, and therefore they are going to be inherently problematic to integrate into microsystems, because microsystems are 2D or 2.5D structures. So that's going to be a first challenge. And you can see, for example, two ways how this is done here. Here you have a coil where it's basically a 3-layer structure. You have a bottom layer with one wire. Maybe you can see that even better in the cross-sectional view. You have a bottom with one wire, and then it goes to a connection to a top layer, and then back to the bottom. So you have below and up, and below and up, and that's how you build a coil. It's kind of in a kind of 2D fashion. And here you can see how that looks like. In more recent development, for example, developments done at KTH, we use a wire bonder. So we make a gold wire and then wire bond it wire by wire around a stem to create a little coil. But this is typically not mass producing, I'd say. Although you can get some throughput in manufacturing this. One related problem to that is that not only that it's difficult to manufacture, like here you'll have to, for example, there's many fabrication steps involved in creating a structure like this. But also, then you only have one winding. So in a macroscopic coil, you typically have many windings, one over the other, to more and more create a stronger field. So here you're going to have only one winding, and well, you have several windings, but you have to lay next to each other. They cannot lay on top of each other. That's what I'm meaning. Otherwise, you can have it will be even more difficult to fabricate. So that means that you're going to be rather limited in the field strength that you can generate with such a coil. So they're not going to be too strong. So far about coils. Let's have a look also now at magnetic materials. The permanent magnetic materials, which are hard magnetic materials, or the low reluctance materials, which are soft magnetic materials. What are soft or magnetic or low reluctance materials? These are materials, very often metallic materials, that have a low reluctance, and that means that reluctance is the analogy of resistivity, but for magnetic fields. So it's going to be they're going to like to conduct magnetic fields, or a magnetic field line will easily pass or likely pass through a low reluctant material. For example, air is a high reluctant material, so a magnetic field line do not like to go through air. But a piece of metal, like iron, will be low reluctant, and magnetic field lines will like to go to iron. How can this be used? Well, we can see a schematic here. This is very typical. This is a magnet, an electromagnet. So we have a piece of iron core here that's U-shaped, and there's a little air gap here. And on one side we put a coil, and we send in electricity through the coil, so we generate a magnetic field. The magnetic field, of course, has to go around the coil in both directions, but because there's this iron core here, it will follow this low reluctance iron core here, and all the field lines will be sucked up by the iron core until they come to the air gap. Here they will be forced to jump through the air gap to the other side, and then here they're happy again. So what happens if you have such a structure, and then I bring another soft magnetic material close to it, is that if I start bringing a material close to the air gap, the field lines will start seeing this and will like to jump rather than going straight to the air, which is difficult for them. They like to jump to the soft magnetic material and go back this way. And they do that because it's energetically much more favorable for them to do so. And you can see the more this soft magnetic material would move into this air gap, the lower the energy of the system becomes, because the easier it is for the field lines to travel from this side to this side. So if we lower the energy of the system by moving this piece from this position to this position, that's the same thing as saying there will be a magnetic force exerted on this material here. It will be sucked into this air gap here. We're going to see an example of, because force is always derivative of energy towards distance. We're going to see an example of that. Hard magnetic materials, they are, as you've seen in the video from Minute Physics, they are materials with a remnant magnetic field, and they can also be used. But first we're going to look at an application of low reluctance material. It's a rather old example here that we can see, but still it's a good one. It's a very pedagogic to show it. This is a relay, an electrical circuit switch. And what we're trying to do here is switch between these two poles. So we have an input port and an output port, and they're not connected. However, there's a moving bar here in between with a T structure, and if this bar is moved this way, it will connect, the electricity will be able to connect through here to the bar and back here. But if the bar is pushed out, there's no electrical galvanic connection, and therefore the circuit is open. So if it's pulled in, it's closed. If it's pushed out, it's open. So how are we going to move this bar here in the middle? Well, this bar in the middle is suspended on a spring structure, and you can see that here. There's a silicon arm here, here, and here. So there's 1, 2, 3, and 4 U-arms that suspend this arm, this moving middle arm, to these 4 fixed posts. So basically this arm can move freely up and down. Well, this is a spring system keeping it in place. And why or when does it move? Well, that is steered by the magnetic circuit here. Here we have a coil that is wound by hand or by a machine. So it's quite expensive actually to build this. A coil, and this coil is built into a magnetic circuit. You see, so the coil lines are forced to this low reluctance material here and back here, and there's an air gap here. And now what happens is that if you put on the coil, you create a magnetic field. And this part of the beam here, of this beam, will be sucked into the magnetic field, because this part is also low reluctant material. It will be sucked into the air gap to minimize the energy here. And by doing so, it will be pulled in that direction, and therefore this blue T here will be, the blue is for the electric circuit here, the blue T will be pushed in here and will close the circuit. So, integration of magnetic materials. How would you go about that in MEMS? Well, that's where it's a bit difficult. Typically they're metallic alloys. How can you deposit those in microsystem? Well, either you sputter them, or you electroplate them, or a third option is to use small magnetic particles, can be nanoparticles or microparticles, that you mix into a slurry, into a prepolymer. And then you put that slurry where you want to have it, and then you polymerize the material, and then you get a plastic-like material that has embedded metallic particles that, for example, are low reluctance material. So there's a number of ways of doing that. However, both the materials and the way of processing them, that means their etching or their machining, they will be typically not be compatible with CMOS processing, and often these materials will often not be allowed into a clean room because they will be poisonous for other clean room processes. So there you have a generic problem. So you have how to combine that with the batch manufacturing inside the clean room. Another issue is that if you want to even use hard materials, hard magnetic materials or permanent materials, you of course need to, for example, deposit the iron, but not only that, you also have to magnetize the iron. And that means that you have to do extra steps once your device is ready, the magnetization, which will cause extra steps that are not standardized, and that will mean extra cost in your production. So more examples. This is a reluctance micromotor. It is built of low reluctance material, again by the group from Guckel. And here the whole frame and these arms are all in low reluctance material. And here they have built 1, 2, 3, 4, 5, 6 coils around. So, and each of these coils, so if you, for example, I put on this coil and this coil, I'll have a magnetic field that goes from this point to this point and then around like this. And so actually they go to both directions, and you can have a magnetic field in this direction, for example. Now in the middle I have a very, very small rotor here. And that rotor has actually only 4 main axes. So if I put a magnetic field between this point and this rotor will rotate from this position to this position, as to minimize because if it doesn't do that, then for example you can see here a lot of the field lines will have to go through this air gap here. There's an air gap here and here. So to minimize that air gap, this whole rotor in the middle will rotate a little bit and align itself to these 2 poles. And you can actually see at the moment it is aligned to the horizontal 2 poles here. See? This is perfectly aligned. That's because the last thing that was happening to this motor is that probably you put a magnetic field on these 2 points. So the rotor is aligned here. Now what you can do is steer these poles one by one. So in couples, first this, then this, then this, and so on and so on. And then this rotor will follow, and you can do that very fast, and you can create a rotating micromotor. This specific example actually could rotate at 150,000 rounds per minute. It has a diameter, this little rotor, of only 140 micrometer. It has an output torque of a whopping 10 to the power minus 7 Newton meter. It's very low. And it also says it is tested for 5 × 10⁷. That is 50 million cycles. That looks very impressive, of course, but 50 million cycles, if you have only 10 million, what was it, 10 million, no, sorry, 150 rounds per minute to get to at 150,000 RPM to get to 10 million cycles, that would take you about, well, what, a few minutes, I guess. You can calculate that. Not so much. So within a few minutes, the system gets stuck. Not so impressive, of course. Also, the output torque is not impressive. So this is nice spielerij. This is work from typically end of 80s, beginning of 90s, where people, well, kind of the rather early days of MEMS, where people were playing around with things. But as far as I know, this kind of systems do not have an application. And of course, you can see very low torque, and yeah, they get stuck also. Nevertheless, Toyota used some kind of these motors to build a replica of the first Toyota. It's a little car built, only 4.8 millimeter long. It has electromagnetically driven stepping motors inside, and it's set to be able to drive 10 centimeters per second. See here, wires for powering it. Good, magnetic actuation in MEMS. So, of course, we have seen so far, we've talked about thermal actuators, and now we talk about magnetic actuators. We will also talk about electrostatic and piezoelectric, but of course, for you as an engineer, it's important to know which principle should I use in what application. So let's look at the pros and cons, the drawbacks, and the good things about magnetic materials. Good things are that magnetic forces can be very, very high. So that's a good thing. Also, you'll be able to have large displacements. That's in contrast to, for example, electrostatic or piezoelectric systems that we're going to talk about later. And sometimes it's very easy to integrate, which is when you use a Lorentz force. Coils are difficult to integrate. Magnetic materials are difficult to integrate. And coils are also, they are not so efficient because they have problems with winding numbers. So in practice, you actually don't see so much magnetic MEMS actuators. But I think it's interesting for you to know that it's possible to use them at least. So before we stop the magnetics actuator part of the lecture, a little quiz. The gyroscope that we've been talking about, is this temperature sensitive? Yes or no? And why is it temperature sensitive? And if not, why not? Well, the answer to the question is the following. What are the principles we're using? We're using an AC current, we're using a magnetic field, then we're using a Coriolis force, we're using strain gauges, and we're using a whetstone bridge. And now we can see which of these principles are temperature dependent. Well, the electrical current is not temperature dependent, the magnetic field is not temperature dependent, the Coriolis force is not temperature dependent, strain gauges, there, Strain gauges are piezoresistors and are of course temperature dependent. So the structure is temperature dependent. However, we've put it in a whetstone bridge, and if we do that correctly, as I've explained, the whetstone bridge will help you to cancel out the temperature sensitivity. So in total, the system will not be temperature sensitive.